want to talk to you about some properties of matrix multiplication and addition. In particular, I want to talk to you about matrix algebra. So, in other words, the algebra of matrices. So I guess one of the most important fundamental things is what plays the role of the number 1 for matrices, the so-called identity matrix. The identity matrix is a square matrix that has 1s down the diagonal and 0s elsewhere. In other words, so I, an element of the n by n matrices. So the identity matrix is defined by the ijth component of it is the Kronecker delta ij. All right. Now, so like for example, sometimes you do a little sub 2 or something to indicate the size of it. So like 2 by 2 would be I2, or maybe I3 would be 3 by 3. Now you notice right away that the columns, or if you want to look at it, the rows, are familiar, right? Like this is E1, E2, E3. So I can prove things about the identity matrix using concatenation of standard basis if I want to. I mean, the proof I have in the notes is a little bit different, but let's just, it occurred to me I could do it this way. It's kind of a new calculation for me. It's not terribly that shocking, or I don't know, what I have in the notes is also fine, but here's a different way to think about it, which uses what we were just doing as well. So it's kind of neat. So if I have a times I, that's really a times this concatenation of the standard basis. So that's AE1, AE2, right? AEN. And what is that? Well, that's exactly by what we were working out just a second ago here in the previous video. That's column 1 of A, and so forth until we get to column n of A. In other words, it's A again. And likewise, IA, well, you could look at that as E1 transpose, E2 transpose, EN transpose times A. But remember, by the row concatenation, that's E1 transpose A, all the way out to EN transpose A, right? But hey, that's exactly row 1 of A, and so forth, which again is A. Okay, so A times I is equal to I times A. It behaves like the number 1. It's like it wasn't even there. Anyway, so an interesting proposition that you can prove is that if we have square matrices A, B, and C in the n by n matrices over a commutative ring, this is my proposition 2.4.4, then if you have AB is equal to BA is equal to I, and if you have AC is equal to CA is equal to I, then you can prove that B, in fact, must be the same as C. Alright, let's see if we can prove that. So assume that AB is equal to BA is equal to I, and AC is equal to CA is equal to I. Consider then that, of course, AB would be equal to, let's see here, AC, right? Because I is equal to I, so this is equal to that. Now, multiply this on the left by, let's say, B. So what I get is I get BAB is equal to BAC. Multiplying out this on the left by B, right? Aha. But then, remember, BA is the identity matrix, so I get I times B is equal to I times C. But hey, we just proved that I times any matrix is the matrix again, so that gets you B is equal to C, and there you have it. This is important because it means the definition I'm about to make is reasonable, and that definition in particular is what we mean by the inverse of a matrix. So definition, let A be a n by n matrix over a commutative ring. Then if there exists another n by n matrix B over the ring, and A times B is equal to I, and B times A is equal to I. Then we say A is invertible. Sometimes we say it's non-singular, and B is equal to A inverse. Now that's not ambiguous because we just proved that if a matrix satisfies those two conditions, it must be uniquely given. All right, so that's an inverse of a matrix. Now, generally speaking, the calculation of an inverse matrix is kind of a bear. This is a special case which is important to know about. If I have a 2 by 2 matrix, A, B, C, D, then there's a neat formula for it. What you can do is you just do AD minus BC. You flip the diagonals like that, and you put minuses on the off diagonals like that. And in fact, that's going to be the formula for the inverse. Now this, we need that, AD minus BC is a unit for this to make sense. In other words, you got to be able to divide by it. Okay? But let's make that assumption and just see why that formula is legit for a second here. So 1 over AD minus BC, D minus B minus C A, and then multiply by ABCD. What do we get? We get 1 over AD minus BC, and we get AD minus BC, and then down here we get minus AC plus AC, that's 0. Then we get BD minus BD, oh I'm sorry, what am I writing? It's 0. And then minus BC plus AD. Alright, so then definition of scalar multiplication, bring it inside, divide this by this, divide this by this, it's the same thing. So you get back 1, 0, 0, 1, and there you have it. It's identity matrix. And likewise, if you calculate A, B, C, D, 1 over AD minus BC, D minus B minus C, A, you'll also get, I won't go through it, but you'll get the same thing, 0, 1. All right? So that shows you that this formula will work in the 2 by 2 case. There are formulas in the 3 by 3 or the 4 by 4 or 5 by 5. You keep going. There are formulas for the higher order cases, but they're so insidiously complicated that only a very, very silly person would try to memorize them. As I mentioned in the notes, his name is Min. Okay, so moving on. The properties of the inverse matrix are interesting. I think I will just write a few of them. So, well, matrix inverse is interesting. So for example, like AB inverse. Supposing A and B are invertible, AB inverse is then given by B inverse A inverse. There's a sock shoes. This is theorem 2.4.8 in my notes on page 40. So there's that is a theorem. If you've got a scalar multiple, supposing it's non-zero and supposing A is invertible, then this turns out to be 1 over C times A inverse. And there's a few other interesting things in the theorem. Like one of the other things is if you have x times A, and you have that's equal to y times A, then that implies that x is equal to y. So we have like a cancellation for invertible matrices, and likewise if I have A times Z is equal to A times W, that implies that Z is equal to W. And transpose and inverse play nicely. The transpose of the inverse is the inverse of the, other way around. So the inverse of the transpose is the transpose of the inverse. There we go. And finally, the inverse of the inverse is the thing again. Now that's pretty much immediately true from the definition if you just look at it. Let me sketch the proof of these things. So to prove this, all we have to do really is just say, okay, so AB times B inverse A inverse by associativity matrix multiplication is A, BB inverse, A inverse, which is what? That's A inverse. But A times I is just A again, so you got A inverse, and so that's I, right? And likewise, you can do it the other way, right? So like B inverse A inverse times AB by essentially the same series of steps is going to be B inverse IB. It's going to be in B inverse B is going to be I, all right? So therefore, by the definition of inverse, AB inverse is equal to B inverse A inverse, right? So if it satisfies those two equations, it means the inverse exists, and since we know it's unique, there's no ambiguity there. The proof of this one, I'll let you work out. The proof of the third thing here, let's just look at that. I'll do it in another color. So I have XA equals to YA. I'm assuming A is invertible. This is all given A and B exist. Okay, that's the precondition of the theorem. Okay, so that implies then that X A inverse is equal to Y A inverse, right? But hey, that's exactly X times I is equal to Y times I, which tells me then that X is equal to Y. Okay, so I think if you understand that, it's pretty easy to see what we're going to do to get that. We just multiply on the left by A inverse, right? I guess that leaves us with the proof of A transpose inverse is A inverse transpose. I'm going to let you look at that in the notes. I'm gonna move along here. I think there's a good proof in the notes. You can decide. All right, so that brings us to the topic of matrix powers. So what do we mean by a matrix power? Like, what should A? First of all, well, A to the 0. Let's define that to be the identity matrix, okay? And then let's define A to the 1 to be A. I think we can all agree on that. Now, if we wanted to define further powers, I would say we should go with the recursive definition, like A to the n is equal to, let's say, A times A to the n minus 1, right? And if A is invertible, we can define negative powers by likewise powers of the inverse. So, so A to the minus p would be equal to A inverse to the p power, provided A inverse existed. I mean, we could define negative powers in that case. All right. Okay, so just once you have that, then you can, prove. And this is just a sneaky way of saying the usual thing. Like you're not going to be surprised when I tell you that A to the 4th is equal to, I can work it out. So that's A times A cubed, right? But that's A times A squared, and that's A times A times A times A. And so you're like, oh, okay, well, duh. Right, but this is a sneaky way of saying that. This is true for all n in the natural numbers. Okay, so there's some interesting properties for this matrix power function. For example, A to the p times A to the q is equal to A to the p plus q. And A to the p to the q power is A to the pq. And also, this is so part 1 and 2 of the theorem, proposition. Well, we can debate if this should be a proposition or a theorem, like I said. These two are given for p and q in the natural numbers union with 0. And then part 3 asserts that these properties 1 and 2 hold true, extend to the to z powers, integer powers. Okay. Now, I give a proof in the notes for I think 1, and it's a little bit involved. I don't want to write it again. Let me just use my notes here for a second. Let me get out my see. Let's see here. Where are we? Basically, I start out by proving that inductively I prove that if we look at a to the p times a to the q, we get, well, here's the proof. So first of all, if you look at 1, it's true for n equals to, true for q equal to 0. I fix p. So it's true for q equal to 0, and then I suppose inductively it's true for some q in the natural numbers, right? Then I look at, in other words, I assume that a to the p times a to the q is a to the p plus q, for some particular q in the natural numbers. Then I look at a to the p times a to the q plus 1. Alright, now, by definition, a to the q plus 1 is a to the q times a. Oh, I'm sorry, I seem to have put them in the opposite order. You could just as well put a on the other side. Sorry. I guess, well, anyway, I'm going to go on. Perhaps this proof needs to be slightly modified to be consistent with that definition, but it's not hard to see how to do that. Anyway, then the induction hypothesis says a to the p times a to the q is a to the p plus q times a, but then that's a to the p plus q plus 1, but that's exactly what I wanted. That's 1 true for q plus 1, so q implies q plus 1. Hence, by induction, we have that a to the p times a to the q is equal to a to the p plus q for all integers. And then I think I leave to you to prove number 2 by similar induction. And what you have down here, then I'll let you read it. But basically, down here, what I show is that let's just agree that we're gonna. Here, I'll tell you what we'll do, fix this. Instead of this being the definition, you fix it right now. This is a to the m minus 1 times a. Now if we make that the definition, right, if we make that the definition, then the proof is right, and we don't have to change anything down here, which would be more trouble. You could kind of go either way, right? Anyway, down here, I show how you can extend 1 to negative integers by doing induction on minus r. Where r is positive. So in that way we do induction on minus r, and that gets us the rest of the negative powers for this rule of algebra. Okay, anyway, I don't think it's especially interesting, but these arguments are, it's important you see them. Okay, on the other hand, this is more surprising. In the case we have two matrices, it is not the case that AB squared is a squared times b squared, right? Because ab squared is actually ab times ab. ab cubed is ab times ab times ab, and if a and b don't commute, there's no way you can rewrite it as like a squared times b squared. However, if they do commute, if you have ab equals to ba, then you do get a to the p, a times b to the p power is a to the p times b to the p. And in fact, the binomial theorem will also hold. Now, I've asked you guys to prove binomial theorem in the scalar case, but once you have that proof, you could easily adapt this proof of the binomial theorem for just a scalar variable to matrices which commute, because they basically behave the same way. Alright, well, I'm going to stop the video here, and then I'll make one other little video to talk about the rest of the things before row reduction. Thanks, guys.